Okay. Uh, Good morning, everyone, once again, and thanks for joining the session. Hope I'm audible. Fine. Okay. So, um, can someone confirm that am I audible fine or not?
Yes, yes, certainly.
Okay.
Yes, Deepak,
Thank
you're
you.
audible.
Yeah. Thank you. Okay. Then let's resume back here. So, firstly, I want to introduce about myself. Uh, myself, Deep. I have industry experience of more than 14 years into DevOps, DevSecOps, and cloud native solution for more than 12 plus years. Uh, the cloud native solution, particularly, I'm working or on for more than 7 plus year, where the major platform is related to GKE or EKS or the on-prem based Kubernetes uh, cluster for production environment, and when we talk about development environment, so it's Docker or any other container runtime. Today I'm going to present a brief demo about containerization. So uh, the agenda for this is to cover the containerization at brief level and what we want to uncover during the batch itself. I will be assisted by some operation team member as well, and they will assist you in terms of any queries, or if there is any technical queries, definitely we can answer that. But for the sake of this demo and timeline, firstly we want to cover this, and at the later part of the discussion, we will take all the queries. Okay, and let's start on this. So. Uh, so, prior to the containerized world, so um, we this is something here I'm trying to cover the background around prior to containerization world. So prior to the containerization world, there is a bare metal infra servers that are present, and that is still present, but it is actually where we hosted our application on top of that. So when we talk about bare metal, so it is a physical hosting device that's dedicated to single tenant, and that single tenant can consume all the resources of computing resources like CPU, RAM, disk space, bandwidth. Okay, and that is dedicated to single tenant only. That data center may be at on-prem at particular organization location, or it's they can leverage the facility of rented data center as well. The need of the bare metal server is that where we need the high level of processing power, the consistent input output operations, high level data security, and we wants to control the cost in a predictive manner. So that's the need of the bare metal infra server. This is one of the snapshot from the open source. So here you can see a lot of bare metal. The servers are stacked at one location, a data center. Okay, move to next slide. Next slide. So it is about virtualization. So the virtualization, it is a next level thing to bare metal server, where we have a physical instance, and it's virtualized with the help of software solution called hypervisor. The main feature of virtualization is that it is virtual in nature, and uh, all the resources allocated to single instance that is shared across multiple virtual instances. We can install multiple guest operating system on those virtual instances, and each operating system has an abstract layer with other operating system. All these things approach applied with the help of hypervisor. There are a lot of hypervisor solutions available in market, like Zen hypervisor, uh, VMware, GCMU, and KVM. So based on the need, we choose our hypervisor and apply the virtualization. In contrast to bare metal server, here you can see that the physical server, these are the physical server, and they are using the facility of shared storage. But on top, we have virtualized server with the help of hypervisor, and we are installing our operating system on top, and then dedicated application. So we have three virtual machines, okay, on top of these collaborated instances. Next slide. There are certain benefits with virtualization. So it is shared across uh, and
Deep, sorry to disturb you, Deep. We're seeing that it's the only the first slide. I mean, the slides is not moved yet.
slides
Yeah.
are not moved.
Yes, yes. We
Okay.
are only seeing the first slide.
Oh, sorry about that. So I need to share my full screen. Just give me a moment. I thought it's visible. Hmm. Okay. Just let me know if it is visible or not. This was the first.
Yeah.
This was the first slide, right?
Right, right.
And are you able to see this?
Yeah, we're able to see the second slide now.
Okay, cool, cool, thanks. So this is like this is something I talked initially about the bare metal server. So what's the bare metal server and what's the need and the typical one example of a data center where we stacked all the bare metal infra servers. In the second slide, I was talking about like the virtualization, the next level of thing beyond bare metal server. So the key features with virtualization, like the shared compute resources, multiple cast operating system, abstract layer between all the operating system, which is installed on top of instances, and everything is achieved with the help of hypervisor. And then this picture depicts like how that actually actually set up on top of physical instances. Okay, in this slide, I just started on the advantages part. So let's resume from there. So uh, the advantages of virtualization is that because of its shared nature, so it's lower cost of management and support. It is flexible. We have a better control. The support person, support team itself has a better control on those virtualized instance. The deployment would be faster, productivity would be increased, and easier backup and disaster recovery. So that means like we can create a backup either in a daily, weekly, or bi-weekly or monthly manner. And in case of disaster, we can simply roll it back to that instance. And there is one particular thing related to environment sustainability. So this is something a buzzword at the moment running. So where the resources, so we are talking about a lot of leaders are talking about the resource consumption, whether it's a CPU, memory, storage, and like depend like and it's impact on the environment. So in case of virtualization, we are also supporting that because we are utilizing the shared resources and consuming as per the requirement only. Uh, There's certain type of virtualization uh, that is like we can start with desktop. So desktop with the help of hypervisor, we can simply set up the remote instances. Server, although I talked about server a lot, but yeah, server is mainly where we can create multiple instances based on our need. Application virtualization, where we can create a virtualized set of application and that can shared across multiple application or multiple virtual instances. storage, one storage we can create, and then that also virtualize and shared across multiple instances, data, and network also we create a some one network setup, complete network configuration, and then shared across multiple virtual instances. So these are the typical type of virtualization. Um, there's a key difference I want to depict here. So here you can see in this traditional architecture where we have one particular instance and all the compute resources are hosted on top of that, and then there is an operating system and on top the application. Whereas in case of virtual architecture, you can see the stack of servers. On top of that, we have virtualized layer. Then we have operating system, and on top app. Another example you can see here, it's a single tenancy where we can see it is the example of bare metal server, and uh, in case of multiple tenancy, this is the perfect example of virtualization. So we uh, okay, just give me a moment. Sorry, move to move to next slide. So again, just try to depict here in terms of the key pointers like. Um, uh, so these pointers would define the differences between bare metal and virtualization in detail. Um, so let's cover some of the pointers. So main selling point of bare metal server, it's consistent performance and complete data privacy, because that is dedicated to single instances. So that's why we can achieve with the help of bare metal server. Virtualization, so it's a near instant scalability and cost optimization option because of its shared nature. When we talk about hardware dedication, so all the resources allocated with single instances in case of bare metal, but in case of virtualization, it's shared across multiple tenants. Performance capability, bare metal, so all the resources intact with single instance, so it's a high performant. In case of virtualization, it's shared across multiple instances. Customization option. So bare metal, we have flexibility to choose our hardware and software, and based on our need, we use to gather those. But in case of virtualization, so we need to control those resources and those customization. Deployment time. So when we need to build something in or ask for bare metal server, it will take some time to get the required subscription or get the right set of servers or infra. But in case of virtualization, it is frequent, and we can get that easily or within small amount of time. Maintenance. So in case of bare metal, it's a managed service, need to be managed with the managed service or specialist who can assist to manage or help with hardware maintenance. In case of virtualization, we need not to bother about hardware. So whosoever is managing that data center, they need to manage that. Scalability, scalability where it's time consuming for bare metal server, but in case of virtualization, it is near instant. Capacity optimization. So in case of bare metal, so it's providing a limited capacity optimization option, but in case of virtualization, we can increase our capacity. Bare metal, it's more secure in nature. Virtualization, because single instance shared between multiple virtual instances, so it's secure in terms of uh, that layer itself. Recovery for bare metal, it's a time consuming thing. If in case any disaster happen, it takes some time to roll it back to previous stage or working stage, or it take more than a day sometime. But in case of virtualizations, we have concept of image and backup and all those things, so it is moreover it's uh, like it's within an hour or within a minute we can easily roll it back. Portability is a challenge with bare metal, but in case of virtualization, we can easily create the images, and then we can port out according to our need. Billing again, so uh, bare metal is most of the time it's a kind of a predictive billing. So we are using the same set of resources, so we know that like what kind of bill we will get by the end of the month. But in case of virtualization, based on the need, we scale up. So those charges also uh, again going to the higher side. So that need to be managed. Uh, for on-prem, if we are hosting on-prem all the resources bare metal server, so it's the management and the managing of those and supporting and upgrade and maintenance. So everything is taking its own cost. But in case of virtualization, so we just need to work with the smaller hardware instances and then virtual utilize the virtualization feature. Okay, so despite having advantage over bare metal server, so virtualization has some sort of limitation as well, and that limitation uh, has given the opportunity to containerization. So uh, in this slide, we are trying to cover those limitation like portability. So portability is one thing like where we want to port out our output or artifact from one or in terms of image, in terms of the complete package. So that is a challenge with virtualization. So we need to create an image and then port out that. So uh, in the later slide, we will cover that how we are achieving with the help of containerization. But at the moment, we just try to cover that. Like that's the challenge with the virtualization. Application dependency health. So uh, there are a lot of application where we need to manage a lot of dependencies, library-based dependency during the package creation itself, and it is quite challenging when we are introducing OS layer dependency as well. So that is with virtualization, it comes automatically. So uh, we need to resolve that dependency to take it to the next level. Return on investment. So when we invest something for in virtualization, so that is taking its own time to provide that return on investment. Security concern due to multi-tenancy. So that is because we have multiple we virtualize instances on top of one single instance. So still there are some security concerns. Scaling challenges, although it's better than metal server, but still there it is a challenging part to achieve that. Hypervisor, so it is a software solution, so there are some sort of performance issue with hypervisor, and hypervisor although supporting them by providing fixes, but still the performance issues are there, and that is creating sometime problem at virtualization level. The single point of failure. So, although this can be managed with the help of better backup and disaster recovery, but still, if we have single instances and then we need to roll it back for with the last set of snapshot images uh, to work in a smooth manner, and that is taking its own time. Back to next slide, virtualization versus containerization. So uh, here we can see that the virtualization, so we have storage, we have either it's on-prem, either it's cloud, and on top of that, we have hypervisor, and then on top of we are installing our operating system, libraries and bins, and then install the application. Whereas in container, we have infrastructure, then on top the operating system, we have container engine. We will cover this in detail in coming slide, but container engine, uh, it's we can say that it is the minimal set of unit which is required for container execution on any platform. So we have container engine, then on top we have libraries and mains, and then application on top. Uh, here, like similar to bare metal versus virtualization, I try to cover the what's the major differences between virtualization and containerization. So the technology, in case of virtualization, it's shared a single instance shared for multiple virtual instances. In case of containerization, the application development, um, the host now with same OS, same machine execute flawlessly on multiple environments. So how we achieve with the so we can achieve with the help of images and all sort of like images. It's a bare it's a read only attribute file for Docker container itself. We will cover that later on. Boot time, it's taking more time to spin up the virtual instance, but in case of containerization, it's taking minimum like between 2 to 5 seconds, but depend upon the dependency, it takes some more time as well, but it's very less than what virtual instances are taking up. Virtual execution speed, so it's a virtualization has its own operating system and it's a resource heavy, so it's slower in nature, but container are faster in nature. The VM instance, it's larger in size. Containerization, it's smaller in size. The implementation cost, it's higher for virtualization, but for containerization, it's very low. Um, the, m- the background implementation concept is that the hypervisor majorly virtualize the underlying hardware for multiple tenancy, and containerize virtualize the operating system by using container runtime. The popular container uh, examples are Docker or uh, and Containerd and Kubernetes for production scale uh, container orchestration. We will cover that in detail later on. Scalability is a time-consuming thing in case of virtualization, but it is near instance based on the need. We can achieve that in containerization. Portability, it's a lengthy and time consuming, but it is very quick in case of containerization. We just need to port that image itself, and wherever that container runtime available, we just simply need to start the container by utilizing those images. Persistent storage, so the virtual hard disk for local storage, most of the time associated with single VM, but we have flexibility to use the shared storage solution as well. In case of containerization, so we can utilize the same principle, the persistent volume, but there are two key items: persistent volume, that where we are uh, gathering the some sort of storage from the available set of resources, and persistent volume claim. So that claim can be integrated with the help of container running container itself. Load balancing. So load balancing can be achieved with the help of a lot of solution available. Uh, Primarily, we were working with F5 based load balancer, and that is something we can utilize for active, passive, or standby kind of setup in case of production, and that can help of the backup and disaster recovery. Uh, in case of containerization, so like the load balancing, it's again we can uh, utilize with the help of mm, load and availability and the orchestration, how the orchestration managed internally. So we will discuss about the Kubernetes cluster. There we have like how it is managing the load and availability, and on whatever the endpoint exposing with the help of Kubernetes, so that is exposed map with the load balancer later on, and um, that manage the public whatever whosoever exposing those services at a public level. Now here in this picture, I'm trying to cover all three items. So the bare metal, you can see the dedicated hardware, host operating system, then application and database. In case of virtualize the hardware, host operating system, then hypervisor as a solution, and then On top, we have virtualized machines. In case of containerization, so hardware, host operating system, container engine, then we are creating or spinning up the container. Back to next slide. So there are some benefits from containerization. So it will increase the portability, scalability. The deployment is taking less time. Productivity is also increased. It is more secure in nature. There are certain set of principles we need to apply with containerization. But yeah, by implementing those, we can get a better security. It's resource friendly. This is something which depicts so why container are lightweight. So although this we talked about this VM, that guest operating system, then bins and libraries, and then on top we have applications. Whereas in case of container, you can see here application A and binaries and libraries are there, and then we can simply create the container for application A on top of that. And there is one more slide where yeah, I will cover that later on, where the changes we are applying in the contain in the Docker itself. Okay, uh, the application pattern use cases. So this is something the typical application pattern or architecture we are getting nowadays. So priorly or most of the time we used to hear about the monolithic application we or with the entire architecture application where we have a web layer, app layer or data layer, business logic layer, and database layer. So those application we call it monolithic in nature. So uh, in case of Java, there are like the jar var model where we need to deploy jar on particular app instances, var for the web instances, and like for supporting those, we have database in the background. So those application we are calling monolithic in nature. The monolithic application can easily deployed on the virtualized instance, and even nowadays you can see that we are spinning up our cloud instances, whether it's a GCP-based VM or AWS instances, and on top, by following some architecture principles, we are deploying our monolithic application, or by following the entire architecture and deploying there. Then this is about the microservices. So the microservice it is loosely coupled in nature, where it is exposing some sort of APIs or endpoints as an output. So here you can see that the user interface is here, and it is getting all the required set of data from the microservices 1, 2, 3, and 4. And at the backend layer, the database is also present. So the containerization, it is the best suited environment for the microservice application, where we just need to um, utilize the base image, and on top packaging with all sort of library and binaries, and then deploy our target service. Come back to the next slide. So introduction to Docker. So in this slide, so here we prior to this, we were discussing about the containerization. Now we are talking about the most important containerization tool. It's Docker. The need of Docker actually it arises from the development mindset, and um moreover, developer can easily control whatever required in terms of the Docker container preparation. So Docker is a platform for developer and sysadmin to develop, ship, and run application based on container. It doesn't mean that the sysadmins are not required, but uh, like the Docker file creation, and then creation of images, and then creation of container by utilizing those images. So all these things uh, created a mixed philosophy of DevOps. So developer plus operations. So um, Docker is a perfect example where both the teams are working in a correlated manner. So Docker is an open source tool, open source containerization tool. It's mainly created in Go and originally on top of LibWord and Alexi. LibWord, it is a managed set of APIs which is utilizing the feature of all the well-known hypervisor, KVM, VMware, Zen hypervisor. Docker simplifies and standardizes the creation and management of container. So this is from the Docker uh, official Docker site. So this is the Docker image you can see here. So you can see the contain in the form of container. It's on the top. It's stacked up. So these are the we are this is something from the official Docker page itself. This is again from the Docker community page. So you can see here we have either physical infra, virtual infra, or cloud infra. Then on top we have any OS, Windows, Linux, then Docker, uh, and then on top we have any platform of application, ASP.NET, Java, Node.js, uh, but and we just need to resolve the dependency by utilizing the container runtime and build our image, and then we just need to push that image to particular registry. We'll talk about that registry later on. So you can see here the flow from the dev to operations are going on. The architecture of Docker. So here you can see I was talking about the Docker container runtime. So uh, the Docker daemon is here. The containers are creating images with the help of Docker client, all the and utilizing the CLI. So we execute some sort of commands there. We'll explain those commands in detail, but this is already these three commands are already here. So you uh, Docker build, Docker pull, Docker run. So you can see here that is interacting with Docker daemon, and then with the help of Docker build, what we do, we are creating an image by using the configuration from Docker file. Okay, when we need to run any Docker on particular instances, we execute the command Docker pull. Pull the images from the registry, and if Docker run we are using for running of container. So Docker run, it is internally calling pull itself also. So when you execute Docker run, it's pull the image, dedicate a target image, and then create the container by using uh, Docker image itself. You can see here whatever the packaging we are doing or defining in the Docker file. So we create our image and push that image to registry. Okay, so there are popular registry Docker Hub. It is a like a Docker registry. It provides both options, either private registry or public registry. So a lot of contribution are doing by like a lot of people who are contributing on the base image creation and pushing those images to the Docker Hub. So we can easily fetch those images, and then on top we do our own customization. So and similar to Docker Hub, each cloud has their own set of registry as well. In GCP we have GCR, in AWS we have ECR, and we can set up our own registry as well by utilizing the Nexus. So Docker system flow. So Docker file, it is the base of the the container creation or the image create. It is the first line we need to develop uh, the some set of steps there So to build up our container. So here you can see that we have written a Docker file, and it is available in source code repository. Then we do the Docker build. It create the image, and then we are pushing that image to our Docker container registry. On the hosting platform, we are pulling that image and running the Docker container itself. This slide cover up the changes and update it. So when we do any sort of changes or do the customization on top of that, so here you can see we have base container image, we have application A, then container A. We mixed, merge all those things in one particular Docker file, create the image, push to Docker image registry. So uh, let's assume that we need some update need to be done as part of application development. So we again do the customization, then our application got updated, and with all those bin packages, it is going to run on the Docker platform itself. Okay. These are the main component of Docker. The Docker image, it is the basis of Docker container. It represents the full application. The Docker container, so we can say it is the executable. The Docker engine, it's provide a base for Docker containers. So create, ship, and run Docker container deployed on a physical virtual host locally in a data center or cloud service provider. So we just need to install Docker or install Docker related uh, configuration, Docker related item and configuration things on platform, and then we can utilize the feature of Docker there. Then the registry service, I was talking about the Docker Hub, and both public and private in nature, but we do have, based on the cloud vendor, they have their own registry as well. Was talking about the Docker image earlier, so this is something about in detail about Docker images. So the Docker images, it's mostly read only template. Okay, and uh, it's built by even single person or some other users, and we can utilize those whatever published in Docker Hub, and we pull that image as a base image and do our own sort of customization. It include most of the time application, all the dependencies, libraries, and binaries, and all the configuration file we needed. Okay, so here in this image you can see that the read layer, it is during the runtime. By utilizing the image, we can't do much changes. That's why it's a read only file. We If we need to apply some changes, then we need to apply those changes with the help of Docker file only, and then we need to create new image and push that image to registry and utilize that image for our container execution. Okay, with the help of Docker image, we are able to create our Docker container. So you can see here, uh, it's isolated application and container. It's it's an output from the image itself. It depends upon one or more images. Based on the requirement again, and Docker container launched from Docker image again. Uh, when Docker container runs, so it's add a read write layer on top of the image. So it means whatever the container is running at the moment, so we can do our own customization, and then if we want to create the image by utilizing that customization, we can simply create the image and push to GC, so image repository registry, and then utilize that registry, that image itself for our next level of containers. Okay, so there is another perspective here, Docker image versus container. So Docker image we can assume as a class. Docker container, it is a instance of a class. In this image, you can see here like all the layer of any any container. Okay, so we have Debian, we have Busy Books, we have images, we have then container, writable, and then on top we do our own customization, adding Apache, adding Emacs, and writable units there. Okay, Docker images and container. So Docker will not only share the base image between container, it also share the same layer between different images. Means with this example, you can refer that there is an operating system, then on top we are using PHP based dependencies and PHP application code. And we are creating a image by utilizing uh, the same operating system, but we have a different code base. Similarly, in this example, we have Node.js as a different application, but we are utilizing the feature of operating system, and then depend upon the requirement and configuration, we are again packaging a different unit for Node.js. This is the example of Docker host. You can see it is uh, lot of containers you can see here, and the images, the node, PostgreSQL, Ubuntu, Docker daemon. It is a Docker run. It's a runtime container runtime, and the volumes. It is the most important part of Docker, the Docker file. Okay, so here you can see in this example, we are using one base image, Alpine image from the Docker Hub repository. Okay, and then on top of that, we are installing the all the dependencies related to Python, and then we are upgrading our Python, and then line number 11, 12, we are installing Python modules again. Then line number 15, 16, we are whatever required from application point of view, those application specific changes we are copying in target doc container. And then in line number 19, we are exposing our and the port itself. And line number 22, we are starting the container CMD, and there are besides CMD, you can see entry point somewhere as well. We'll explain that in later on. But yeah, most of the things like here we are starting the our container. And yeah, Docker network. Docker network. So in this Docker network, so we have will have a network infrastructure. The network drivers are there. Then on top we have Docker engine, then networks. So based on the requirement, we need our network to be configured. So for that, we have a Docker driver network drivers available. So bridge network is one where it comes in a default in nature. So all the internal IP address are if wherever it's required for private internal communication. So there we are utilizing bridge network. So it's by default in nature. Host network. So something we want to expose from our container. So there we need to configure with the help of host network. None. So we just need a standalone container, and we don't want anything to configure in term, or anyone can access that. So we utilize the none. Overlay. So most of the time till now we were talking about the standalone container. Mm, Uh, from the next slide onward, we are going to talk about the clustering on multi-cluster environment. So there we need will have a overlay network for Docker Swarm cluster. So that the overlay network is covering all the like external layer of all the container integration. So here you can see that in the bottom example, the single host network, there are drivers and bridge host and none based on the requirement. But in case of the multi-host networking, you can see driver, the overlay network. We'll explain in detail. These are the popular Docker commands, which is we are using in a day in day out basis, and this is something. Uh, a handy item for running a Docker container. Once all the need-based like images and Docker file, it's up readily available. And so the most important commands we can say here, Docker run image. We can provide our container name itself. Then if we want to expose or map our port, so with the help of -pp, we can do that. We can start our container in the background, and then we can assign host name as well. uh, Managing, so once our container is in running mode, then we need to manage that container itself as well. So with the help of Docker PS, we can execute the list of or get the list of running containers. And if we want to remove that, we can remove with the help of Docker RM. For Docker image removal, so we can use Docker RMI. For image pulling, Docker pull, and pushing that image to registry, Docker push. And these are like related to operation side, where we need to fetch the log and take it like do the debugging or runtime analysis. Okay, refer this. It will help in terms of like gathering all the commands at one place. Okay, so we were talking about the standalone container. Here we are talking about another option we have with Docker is Docker Compose. In case of monolithic, we were talking about the entire architecture, but Docker also provided the feature of Docker Compose, where we want to run multiple instances, and resolve with the help of some sort of dependencies. So let's suppose we need to built a container, two-tier architecture container where we have one database and application layer. I will explain in detail, but in this picture you can see if we just from the development point of view, if we want to build a single container, that's fine. But if we want to build for in a like a for a multiple layer, it will break. So we need to utilize the feature of Docker Compose in that case. Hmm. So this is the tool for defining the multi container. So we define all the configuration item in the form of Docker compose.yaml, and we need to execute some sort of command for Docker from Docker compose, and that will help us to build up the container. So in the first example, you can see here that we are explaining the Docker compose file version, and then we are building up the services, and we are using the Redis image for building up the database, and with the help of build, so we are going to build our application and exposing the port. In this example, the second example, we can see here uh, we are building up on PostgreSQL. Okay, we are building up our PostgreSQL, and on top, and then we have our application also, and there is one particular tag depends on tag, so db. So it says, it means that will be will start uh, application will be start only once db is up and ready. So that kind of a dependency we can establish with the help of Docker Compose. Okay, now come to the next level. It is about the container orchestration. So container orchestration is required where we need to set up something at in a production grade. So Docker also providing a one popular component, Docker Swarm, where we do the clustering, native clustering. Okay, and we are managing multiple Docker domains here. So here you can see that we have a lot of containers. This is the official image of Docker, and we do the clustering. Okay, we are not touching in detail about this. We will explain about the Kubernetes in detail. So another orchestration tool is Kubernetes, and that is quite popular. So we'll explain in detail. So now comes with Kubernetes. Uh, Kubernetes, it's a popular the cluster the container orchestration tool, and for all the production grade implementation, you can see a lot of implementation around the Kubernetes in real-time projects. It was initially developed by Google, but later on, it, it's it is available for open source completely, and the lot of open source contribution are going on, but Google is also contributing there. Google has its own cluster um, management, so GKEV, that known as GKE, Google Container Engine. Uh, Kubernetes provide a managing way of managing related distributed component and services across varied infrastructure. The underlying infra of any cluster, so it may be hosted on particular cloud, on-prem, or it may be in hybrid in nature. So some infra hosted on on-prem and something on cloud. So we just need to collaborate at one place. So that's something we can achieve with the help of when we built up our cluster itself. Okay. A Kubernetes platform designed to manage lifecycle of containers applications serviced by using predictability, scalability, and high availability. So Kubernetes, we will discuss about the Kubernetes architecture in detail, but this is the most prominent feature of Kubernetes, where Kubernetes is taking care of most of the things automatically, and you need not to intervene there because it's API driven integrations are there. Okay. So the advantages you can see here. So it's a self-healing, automatic bin packaging, automatic rollout, rollbacks, storage orchestration, service discovery, load balancing, and secret and config map. Service discovery we were talking about that is related to predictability, scalability, and high availability. So based on the need, uh, Kubernetes spin up the pods. We'll talk about the pod later. Okay. Here in this architecture, you can see Kubernetes has two main components. One, the control plane, and another is worker node. And when we talk about control plane, it's again divided into key four segments: Kube API server, Kube scheduler, etcd, Kube controller manager. Cloud controller manager, it's based on the cloud vendor, but yeah, moreover these four items you can see everywhere. When if you want to set up your Kubernetes cluster on on-prem, you can see you need to configure and play around with these things. Similarly on parallelly on worker node, we have three items: kube proxy, kubelet, and container runtime. So we were talking about Docker. So similar to Docker, there are certain other container runtimes also, that's CRIO, and then container D. Okay, and so these things are also available and can be used as a container runtime. Okay, now we'll talk about the core component. I had explained about the four key items in control plane and as well as in worker node. In this next slide, I will explain like the control node architecture in detail. Okay, so Kube API server, it is responsible for API management. So all the integration happening in Kubernetes in with the help of APIs only. Okay, so it is responsible. API server is responsible for API management, authentication, processing of APIs, and uh, the direct byway communication with etcd. Etcd is it's a brain of Kubernetes cluster. Okay, so it actually manages the whole operation of distributed system, and it stores the data in a key value pair. Kube scheduler, there are a lot of scheduling is required when we talk about Kubernetes. So whether the pod is available or not, or um, and there are certain operations need to be involved. So Kube scheduler, it's particularly responsible for scheduling of pod on worker node. Then we have Kube controller manager. So when we talk about Kube controller manager, so it's control the like operations around um, the Kubernetes uh, worker node. Okay, and it interact directly with the QB API server. So there are a lot of controller like application controller, scheduler controller. So when we go into detail, we'll explain those things. But yeah, there are a lot of controllers are there in Kubernetes, and those things can be achieved with the help of Kube controller manager. Okay. Now come to this is another architecture of controller etcd. So etcd, it is as I was talking about, it is a brain of the server. So it is interact Cube API server is directly interacting with etcd. So etcd holding up the information in a key value pair. So you can see a lot of information available here, and these all are Kubernetes objects. So Kubernetes creating some certain set of objects during its implementation, like service account, secrets, pods, namespace, event, daemon set, config map. So everything we are hosting up here. In the second architecture, we are discussing about the controller. So you can see here the what controller actually do. So it watch, it update. So moreover related to the pods, job, namespace, deployment. So everything managed with the help of controller. These are the object resources which is required for creating those deployments like pod.yaml, job.yaml, deployment.yaml, namespace.yaml. Okay, come back. Next slide. It's about the worker node. Worker node, uh, worker node is a place where actually our smallest unit pods are running. Okay, so here you can see the one most important component of worker node we are discussing kubelet. Kubelet, it is an agent that is running on every node in cluster, and it run as a daemon service. And it is responsible for registering the worker node with API servers. So this integration, so with the help of pods pack. It is also responsible for mounting volumes if it is required any storage, and any operation related to container. So that is also done by kubelet only. Everything, whatever we are defining in pod spec in the form of YAML and JSON, so that is managed by kubelet only. Okay. Uh, there are some policy. There are some certain features like liveliness, readiness, startup props. So that is also managed by kubelet. We'll explain in detail later on. This liveliness, readiness, and startup prop that is helping Kubernetes to be to be available in a perfect state. If there is any problem, liveliness, checking the whether the pods are alive or not, readiness, whether the pod is able to serve the traffic or not. So this is something managed with the help of kubelet only. The kube proxy. Kube proxy, it's a daemon service that runs on every node, and it is responsible for exposing the pods. So when we deploy something on Kubernetes cluster, so we need some public endpoints as well. So kube proxy is responsible for exposing those service and endpoints. It is handling the discovery and load balancing. Okay, so in this integration, you can see here the control plane is interacting with API server interacting with kube proxy, and then it's interact with cluster IP, and the pods are exposing the endpoints. Okay, we'll talk about that services in detail. There are three to four type of services in Kubernetes, and what is the meaning of the service? Okay, container runtime. Likewise, in Docker, we in Kubernetes also we need a container runtime on every node. Okay, and that when we talk about the container runtime, so we are utilizing most of the time till 1.23 Kubernetes version, we were using Docker D, but post 1.24 Kubernetes version, uh, we need to switch to container D, but it has the still it has the uh, backtrack compatibility with all the Docker file we have written up in the doc for the Docker. But yeah, Kubernetes version 1.24, we Docker D is not going to be used as a container runtime. It would be container D only.
Bismillah.
Mm.
What's it?
Sorry,
Like,
I'm getting multiple noise. Sorry.
sorry.
Okay. Okay, so this is about the container runtime. So container runtime is required on every node to run the container. So you can see here that we have container host, Linux container, and then we have containers. So CRIO is another flavor of container runtime. Then it is interacting with Kubernetes node, and user interact with Kubernetes master. Okay. Now, okay, I was talking about the Kubernetes most important objects. So try to list out all the objected at one place. So you can see here the pod, deploy, uh, replica set, daemon set, control plane, job, cron job, HPA, namespace, node, service, ingress, uh, limits, quota, PVC. So there are a lot of objects Kubernetes is providing as part of the implementation. In this slide, Kubernetes, it's a widely used across multiple platform, but just try to cover that like the most popular one. So you can see here the remote and edge, then GCP, AWS Azure data center, and you can see Azure AKS. Azure has own flavor of Kubernetes AKS. Google has GKE. Amazon has EKS, and then VMware has then and then OpenShift. OpenShift is a popular product from Red Hat. So OpenShift, it's moreover a wrapper on top of a bare Kubernetes. We can say that. Okay, the popularity chart. So Kubernetes, it is a de facto in industry. We can say that, and it's a prominent tool which widely used in on production implementation across the industry. So you can see Kubernetes, then Docker Swarm, then OpenShift. So you can see that majority of the operations are managed by the Kubernetes only, and it is a slightly old just extracted from open source, but definitely I'm sure that this number has been increased. This is about the Kubernetes ecosystem. The Kubernetes ecosystem, you can see here, the public cloud like GCP, Azure, AWS, IBM, then the framework which is supporting Kubernetes, Red Hat, VMware, Docker, Cloud Foundry, SUSE. Then the tools, particular important tools are there like uh, JFrog, CloudBees, uh, then management of they are particularly managing the Kubernetes cluster for themselves. They have their own setup as well. Likewise, DigitalOcean has its own Kubernetes version. Okay, and then something we can integrate with in terms of security with Kubernetes implementation, like Black Duck for software composition analysis, Aqua, Twistlock. Then monitoring and logging, and there are certain set of monitoring logging also we can apply as part of our Kubernetes integration. So Sumo Logic, Datadog, Prometheus Grafana, App Dynamics. So these are the popular tools which work all along across the Kubernetes ecosystem. So although Kubernetes has its own like based on the platform, it has own load balancing. But when we talk about the on-prem based instances, so we can leverage the load balancing feature of Nginx and HA proxy and like some third-party provider as well. Okay, this is about Kubernetes. So now I'm trying to cover one end-to-end flow of one particular implementation of microservice with DevOps and GitOps. Okay, so here in this slide you can see here. Let's assume developer. This is about the microservice only, and it's not about any other flavor of application. So developer is uh, developing the code and committing the code in source code and repository. Then it create the build, then do the static code analysis, do the unit test, create the build report, and do the package creation. So for container, we need to create the artifact in the form of image and push that image to Docker registry. Then during the deployment process, deploy to container, Kubernetes, and post deployment, it is monitoring and operate and everything like developer and operation and sysadmin, everyone working in collaboration to manage these operations. So here you can see that popular example, the GitLab is here, Bitbucket is here, Visual Studio, then Git, um, then we have Jira, Confluence, and as an artifactory, you can see Nexus and Docker are here. This is particularly from the Java flavor Java based operation. So Maven we are using as a build tool, Jenkins as a CI/CD platform, SonarQube as a code coverage, and JUnit for the unit testing. Another implementation is that about the GitOps, where we can say that the app user is coding and committing the code in Git, do the CI and push that to registry as an output artifact. Once that is ready, then deploy on dev cluster, staging cluster, and production cluster. Similarly, if application configuration, any update is coming up, then again going to Git, then as part of the deployment model, going to dev cluster, staging cluster, and production cluster. Okay, so this brings me the end of this demo.